Okay, so here we talk about the third type of the capacitor called the spherical capacitor. So actually the cross-section area is the same as the previous one, the cylindrical, but actually this one is two coaxial cylinder, So it has a cross-section diagram like this. But here we have two concentric sphere rather than coaxial cylinder. Okay, so although the cross-section view are actually the same, but yeah, originally they are different. Okay, so actually for the spherical capacitor, the capacitance is something like this. Here we don't try to repeat the whole procedure. We don't try to complete the whole procedure. But if you have interest or you can try to practice it at home, whether you can really derive it out. You can just simply try to repeat the step, something like this. You try to write out the Gauss law, and then you try to define the Gaussian surface similar to this. So here we have Q equals epsilon naught EA. Okay, although here the A part is different. Okay, for this part A is different. This one is a cylinder, so the surface here for the side of the cylinder is just this rectangle. But here the A is different. How is it different? 4/3 pi r cube. 4/3 pi r cube. No. This is the volume. The surface area should be 4 pi r square. Okay, it should be like this. Okay, so the cross-section area is different, or the surface area is different. Okay, so this is proportional to r square. This one is proportional to r. Okay, so you can clearly see the difference. Okay, so in that case, if you just try to plug in this one to there, okay, so there will be a little bit difference. So you can just simply imagine that it becomes a dr over r square. Okay, of course the constant in the front are a little bit different, and then the integrate dr over r square, it will be something like this. It will be v equals something times integration of dr over r square from a to b. Okay, so like this, we will see that it is a negative 1 over r. It will be negative 1 over r. So in that case, it becomes something like this, 1 over r, because it turns out to be something like 1 over a minus 1 over b. 1 minus a minus 1 over b will become b minus a over ab, something like this. And then we just move it to the other side, so AB will go to the top, B minus A go to the bottom. Okay, you can somehow see it, although I don't write out the complete procedure, but if you have interest, I suggest you to practice it at home, so that to see if you are very handle how to derive the capacitance. Okay, so this is the C for the spherical capacitor. So 4 pi epsilon naught AB and then over B minus A. Okay, so here we have a special case. The special case is an isolated sphere. For the isolated sphere, we assume A is the smaller radius to be capital R. And then for B, we assume it to be infinity. So which means that we just simply remove the outer sphere， 就是我们把外圈不放了，我就把那个外壳拿掉，只有里面的那个球心，然后把里面的那个半径 A 变成大写的 R。Okay, so in that case, if we just put A to be R and then B to be infinity, it turns out to be something like 4 pi epsilon naught, and then we can divide B so that it becomes AB over B and then B over B minus A over B. Okay, here because v turns to infinity, so B and B cancel. Okay, this one becomes a 1, so and then B is infinity, so which means that this term is becoming a 0. So 1 minus 0 here, okay, it turns out to be an A, and then we just put A to be capital R. So it turns out to be 4 pi epsilon R, okay, to be the capacitance of an isolated sphere capacitance. Okay. Yeah. So here we have a quick check point. So here it says for capacitors charged by the same battery, does the charge stored by the capacitor increase, decrease, or remain the same in each of following situations? 就是说，我们如果有个电池，同样的电池，意思是同样的potential difference， 或者是同样的 voltage。Does the charge stored by the capacitor increase？ 那我们只改变它的尺寸，然后问你的那个电容值会变大还是变小还是不变 ？Okay, so for question A, the plate separation of a parallel capacitors is increased. Okay, so does it increase or decrease? Okay, for question A, C equals epsilon naught A over D. Okay, does it increase or decrease? If we try to increase the plate separation, which means that D increase. Okay, for D increase, so the whole term decrease. Okay, right? So C will increase. C will decrease. C will decrease. Okay, for question B, the radius of the inner cylinder of a cylindrical capacitor is increased. Okay, so for part B, C equals 2 pi epsilon naught L over lateral log of B over A. Okay, so here it says the radius of the inner cylinder is increased, which means A increased here. For A increase, so this B over A decrease, lateral log of B over A decrease. So this denominator decrease, so the whole thing increase, right? So you just need to go through it layer by layer. Okay, so this one increase, this thing decrease, and then increase. So you just assume all the other variable doesn't change at all. Okay, for question C, the radius of the outer spherical shell, okay, is increased. Okay, so here C equals 4 pi epsilon naught AB over B minus A. Okay, so here it says the radius of the outer sphere shell is increased, so which means B increased. Okay, so if we just look at this one, it is not easy to determine because B is related to both here and here. Okay, so this increase, it will decrease, this will increase, this will decrease. So it is not easy to determine. So in that case, we try to do some algebraic calculation. Let's say we try to divide AB here and here. So here we have 1 in the numerator, and then we have 1 over A minus 1 over B, like this. Okay, so here we can easily determined because we only have a B here. Okay, so B increase, 1 over B decrease, and then minus 1 over B increase, and then minus 1 over B decrease, and then the whole thing, this increase, decrease, increase, increase, decrease. Okay, so finally finally decrease. Decrease. Oh, am I too fast? Once again. Okay, B increase, 1 over B decrease, 1 over B decrease, minus 1 over B increase, minus 1 over. So this one minus 1 over B also increase, and then it is in the denominator. If it is increased, the whole thing decrease. Okay, so finally C is decrease. Okay, so far any questions? 能不能跟上有冇問題？Okay, so let's move on. Here is a sample problem. Okay, so here it said switch S is close to connect the uncharged capacitor of capacitance C equals 0.25 microfarad. Okay, I just forgot to mention about the SI unit, the SI unit for the capacitor. So the SI unit of C is what? Is farad, F-A-R-A-D, farad. Although you don't need to remember how to spell it, but it is F. Okay, it is F. C is coulomb, is for the charge, SI unit for the charge. For the capacitance, the SI unit is F, capital F, farad. 多少法拉或者是多少法 femtofarad 不一定 femto 啦，可以是 pico nano 就是 farad. Okay, so this is a 0.25 microfarad to the battery of the potential difference V equals 12 volt. Okay, so this is V equals 12 volt. So the lower capacitance plate, has thickness L equals 0.5 centimeter, and phase are A equals this area, and it consists of copper, in which the density of the conduction electron is N. Okay, okay, so this is the density of the electrons. Okay, from what depth D within the plate must the electron move to the plate face as the capacitor become charged? Okay, 所以这个是一个比较现实的问题，那之前跟你们说嘛，就是一个导体，如果它有电荷，那个电荷的话会跑到它的表面，跑到它的表面。那现在实际的问题是说，电荷它会占空间的，它不可以是无穷的堆叠在一起的，所以它就告诉你说，这个电子它有一个密度，它就是每一个立方米那很大的一个空间里面，它可以有那么多个电子，那所以的话就是说，它可以跑到表面，但是它会有一点点的厚度它会有一点点的厚度这样。那他就问你，如果按照这个密度的话，它的厚度会跌多高 ？Okay, so this is a very simple sample problem, but it somehow tied to the physics itself. So the calculation will be easy. So first of all, we try to calculate how many charge are there. So first Q equals CV. So here C is 0.25 microfarad. So 0.25, 0.25. Micro, what is micro? Micro is 10 to negative 6. And then V is 12 volt. 12 volt. So this Q is simply 3 times 10 to negative 6 coulomb. This is the charge. This is the charge on both the top plate and bottom plate. But we will have plus Q on the top plate and then negative Q on the bottom plate. Yeah, because this is the positive side, this is the negative side. Okay, so positive charge will go to the top plate, negative charge will go to the bottom plate. So this is the Q, and so this is the charge amount. Okay, so here we would like to compute how many electrons are on both the on the bottom plate. Okay, so here we have the charge amount 3 times 10 to negative 6 over 1 times 6 times 10 to minus 19. 19. So this is the elementary charge. Elementary charge. OK， 所以这个是总的负电荷除以这个单一个电子的电荷。OK，so this is 1.87 times 10 to the 13 electrons. OK, electrons. OK， 虽然 electrons 不算是一个单位，就是那我挂号就是提醒它是几个电子几个电子。Okay, so in that way, we would like to use n times a times d equals n. Okay, so this formula is easy to understand. Okay, so this is the total number of electron, total number of electron here. Okay, so there will be n electrons in the orange region. And it tells you that the area, the cross-section area A is like this. And then it asks you how to find the depth, which means the height. The height. Okay, so for this volume, it is nothing but the cross-section area times the height. A times D will be the volume. Okay, so this is the volume, and then this is the density. This is the density. So the density times the volume will become the total number of electrons. Okay, so this is easy to understand. So in that case, we have a D equals capital N over A times small n. So this is nothing but 1.87 times 10 to the 13 power, and then A is 2 times 10 to negative 4, and then times 8.94 times 10 to the 28th power. So it is nothing but 1.1 times 10 to negative 12 meter. OK， 所以这个的厚度的话，就是1.1乘以10的负12次方米，那当然是一个很矮的一个高度，所以我们就很相对比较简略的就说它就跑到表面，但是它有一个厚度，那这个厚度很小。那如果你要写成scientific prefix 的话，它就是1.1 picometer， 那 picometer 就是很小它很小它比一个原子的半径还要小Okay. Okay, so far any questions? Okay, so next, we talk about the parallel and series 就是并联跟串联parallel is 并联，那 series 就是串联。Okay, so first we'll talk about the capacitors in parallel. Capacitors in parallel. Okay, so here we have the circuit diagram. We have the circuit diagram. This is the battery, or we may somehow write it. So we may write this is V plus and minus. Okay, so this is the positive side. This is negative side. And actually, this is connected to three capacitors. Three capacitors. Okay, so this positive terminal connected to the top plate for 1, 2, 3 capacitor C1, C2, C3. Okay, we have C1, C2, C3 here. And then for the negative terminal, they are all connected to the bottom plate for the C1, C2, C3 also. Okay, so this is what we call the parallel 就并联的话，就是正极把就是全连接到这个电容的顶板 top plate 顶板这个接着，然后负极的话也接到底板一个接着，那这个就是叫做并联了。Okay, so in that case, as much as this wire connected to this 3 node, and then this wire connected to this 3 node, so in that case, this potential, so from here to here to here to here, okay, so all the points share the same electric potential, and so as the negative terminal connected to here and here and here, so these 3 bottom plates share the same potential, electric potential. So which means as much as we have a potential difference V for this battery, we also have V. So we also have V here, and V here. Okay, so due to the parallel, they share the potential difference or share the voltage. Okay, so for these 3 capacitor, we can actually write out Q1 equals C1V, Q2 equals C2V, Q3 equals C3V. Why don't we have V1, V2, V3? Because, just as what I mentioned, all these 3 are shared by these 3 capacitors. 就是因为它们并联的话，它们3个的 potential difference 都是一样的，所以我们不需要写 V1, V2, V3。那你要写V1, V2, V3 等于 V 也是可以，但是我们就不要引入太多的太多变数它一样的你就写它一样就好。你硬要定义很多的变数，你只会把自己搞乱。我很久以前当那个电路的那个助教的时候改考卷，就是他们一个电路，然后每一个符号都定义出来，就是所有的电流都定义5个，然后电压又定义10几个，然后写出几十个式子，然后大部分式子都是自己跟自己打架的，那就没用。所以如果是同一个符号，你就写同一个符号就好，那就自己反而不会混乱那这个 V 都是它们是共通的，那就写 V 就好。C1, C2, C3 它们是3个不一样的电容值，然后那相应的 Q1, Q2, Q3 它们也是不同的。Okay, so in that case, we try to find the equivalent circuit. 我们找一个叫做等效电路 equivalent circuit。这里有一个 equivalent circuit 就是等效的意思。等效是什么意思？就是如果我们把这个3个电容换成另外一个电容 然后如果看到一样是什么意思？就是存在这里的电荷一样，这里的电压也一样，那我们就会把它称为是等效啊。虽然它们不是一模一样，这里是3个电容，这里是1个。那如果这里把3个换成1个，但是它们的特性一样的话，我们就把它叫做等效。So in that case, we try to replace these 3 capacitors to be a 1 CEQ, to be the CEQ here, so that if I give a potential V to be the same, then this plus Q will be the same as Q1 plus Q2 plus Q3. Then we will say these 2 circuits are equivalent to each other. So in that case, we have Q equals Q1 plus Q2 plus Q3. This part is due to the equivalent. So here we try to plug in Q1 to be C1V1, Q2 to be C2V, Q1 to be C1V, Q2 to be C2V, Q3 to be C3V. So clearly you can see that V is the common factor, so that we put this V outside. So we have a C1 plus C2 plus C3 in the parenthesis, and then all multiplied by this V. Okay, so if we just look at Q equals this part, okay, we have something like this. Q equals C1 plus C2 plus C3 times V. And for this one, we can simply write it as Q equals CEQ times V. Okay, the V will be the same. So actually here, if you simply compare this formula with this one, Q and Q are the same, V and V are the same. So that which means that these parentheses C1 plus C2 plus C3 should be equal to CEQ. Okay, so that's why CEQ equals C1 plus C2 plus C3. Okay, so this is for 3 capacitors in parallel. If we have n capacitors in parallel, we will write it as CEQ to be summation of Cjj from 1 to n. Okay, so for parallel capacitors, simply speaking, we just add the capacitance together to be the equivalent capacitance. So here the highlight is capacitors connect in parallel can be replaced with an equivalent capacitor that has the same total charge Q and the same potential difference V as the actual capacitors. Okay, simply speaking, you just add the capacitors for the parallel capacitor. Okay, so next is about the series capacitor. So for the series capacitor, the circuit is a little bit different. Okay, so we try to connect this C1, C2, C3 back to back. 就是头跟尾接起来 Okay, so in that case, the battery, the positive terminal of the battery connected to the top plate of C1, So the bottom plate of the C1 connected to the top plate of the C2, so on and so forth up to here. The C3, the bottom plate of the C3 connect back to this negative plate. Okay, so in such a way, this total potential is V. This is V1. Okay, so V is here to here, V1 is here to here, V2 is here to here, V3 is here to here. Okay, so you can imagine, okay, you can have V1 to be from this path to here, okay, is V, and then this one from here going through this path. So V should be V1 plus P2 plus V3, okay. So this is due to the potential, only related to the starting point and end point. It don't relate to the path. So for path 1, okay, for path 1 is only V, okay, and then for this path is V1 plus V2 plus V3. So these two sides should be the same. And here we don't have sharing V for the capacitance. So in that case, for C1, C2, C3, we have different potential difference, V1, V2, and V3. But here the sharing variable is the charge amount. So here we have positive Q, negative Q, positive Q, negative Q, positive Q, negative Q. Why will be like that? If you don't have the battery at the beginning, okay, so just imagine if we have C1, C2, and C3, something like this. You just connected to nothing. Okay, and in that case, there won't be any charge. Inside. So in that case, if you have a battery here to charge the capacitor, here starting from here, we will have positive Q, and due to it is a capacitor, if we have a positive Q here, it should have a negative Q here. But in this part, we don't have any excess charge. Okay, we don't have any charge. The charge cannot go in or going out because this part is totally isolated from the outside. Okay, there is no charge can go in or go out. So the total charge should remain 0. Okay, due to the conservation of charge. So as much as we have negative Q here, so we should have positive Q here, so that the total charge at this part will be 0. Okay, so on and so forth. This is positive Q due to this is a capacitor, this is negative Q, and then here for this part it should have a total charge of 0. So negative Q here, positive Q here, and similarly this is a capacitor, positive Q, negative Q. So which means that we have the sharing variable to be Q for the three capacitance. So we have a V1 to be Q1 over C1, V2 to be Q over C2, and V3 to be Q over C3. Okay, sharing variable of Q. And then we try to plug in these three equations into here. So we have Q over C1 plus Q over C2 plus Q over C3. And clearly we can see that Q is a common factor. So we just put Q in the front. Okay, we have a 1 over C1 plus 1 over C2 plus 1 over C3 in the parentheses. So V equals this Q times this big thing. Okay, so we just look at here and here. Okay, and then similarly, we try to replace this part, okay, to be here. Okay, so we try to call this part of the equivalent circuit. Okay, replacing these three capacitor in series as this single equivalent capacitor. Okay, so based on this, we can simply write it as CEQ equals Q over total V. Okay, this total V is the same as this one. So in such a way, if you just look at this equation with this one, okay, V equals this thing, okay, you can actually write it as V equals Q over CEQ. Okay, so this V is the same as this V, this Q is the same as this V. So this CEQ should be the reciprocal of this parenthesis, 就是这个挂号的导数啊，这个挂号的导数。So CEQ is here equals to 1 over C1 plus 1 over C2 plus 1 over C3, like this. Or similarly, we just take the reciprocal on both sides. We have 1 over CEQ equals 1 over C1 plus 1 over C2 plus 1 over C3. Okay, so finally, here is the highlight capacitor are connected in series. 是串联的电容 can be replaced with an equivalent capacitor that has the same charge Q and the same total potential difference V as the actual series capacitors. And the series capacitance will be the reciprocal. You take the reciprocal of the capacitance and then you add all of them together. And then take the reciprocal again to be the series capacitor. 就是先取导数加起来，然后再取一个导数，它就会是一个串联的电容。